The work I'm talking about is set in discrete optimization, so it's quite a bit of different flavor than most of the talks we have heard. But on the plus side, it's very, very simple. So I have no theorems no one knows about. Actually, I have no theorems at all, so it's very easy to follow. So hopefully it will be still interesting to people. And this is joint work with Lena Gorelick, Yuri Boykov, Ismail Ben-Ayed, and Andrew DeLong. And I would point out Lena Gorelick, who did a lot of work contributing to this talk. So I'll start by introducing the discrete framework we are working with. In particular, my talk is about optimizing pairwise binary images. I'll talk about submodular images, those which are easy to optimize, but the main topic of the talk is optimizing anti-hard images. So I'll first talk about approach we developed a few years ago based on locally submodular approximation for such images. And in particular, we adopt two very well-known frameworks in continuous optimization, trust region and auxiliary function for this problem. And then in the last part of the talk, so it turns out trust region is a better method. It gets us better results, better images, but auxiliary function is a faster method. So in the last part of the talk, I'll talk about taking this inferior method, but much faster method, and making it perform much better, getting the results which are as fast as the original, but often in most of the cases beat the trust region-based method. So again, as I mentioned, I'm working in the framework of discrete optimization. So I'll introduce a notation, and the simplest example of discrete pairwise binary energy on this simple task of segmenting an object from the background. So suppose we have this image and we want to segment an object from its background like that. So it's the llama. So we're going to, our aim is to assign to each pixel p in the image a variable xp. And since we are dealing with binary images, xp, variable assigned to pixel p, is restricted to have two values, 0 meaning background or 1 meaning foreground. So we formulate the following image, which has two terms. So all the variables we assign to pixels, we're going to collect them and store them in vector x. So x here is the collection of all pixel label assignments. And we are going to put an energy which we want to optimize. It has two terms, two commonly used terms, data term and smoothness or regularizer term. First term is the data term. So we're going to express it in the following form. For each pixel p, we have coefficient fp, which tells us whether this pixel prefers to be foreground or background. So here is visualization of all fp's in this picture. So again, f is vector which collects all fp's. So here, whenever you see, so whenever fp is negative, it means pixel prefers to be foreground, because foreground, you assign 1 means foreground. So if fp is negative, you actually want this pixel to be assigned label 1. And if fp is positive, this pixel wants to be background, because then assigning 1 is costly, you want to assign it 0. So here's the illustration of fp's. So whenever you see bluish colors, these are the pixels which want to be foreground, and reddish pixels, these are the pixels that want to be background. And of course, this data term is not enough. We have to regularize it. So one of the most popular regularizers in discrete optimization is POTS model. And for the POTS model, all you do, you go over nearby pixels and you compare the labels assigned to these nearby pixels. If they're not the same, you have penalty VPQ. If they are the same, there is no penalty. So this penalty VPQ between nearby pixels usually depends on the contrast between them. So if there's an edge between these two pixels, the contrast is strong and you don't penalize discontinuity quite as much. So this is done to align image discontinuities to the boundaries. And here's the segmentation you will get for that example. And of course, global optimum you can find efficiently with a minimum cut. This type of energy is very popular for segmentation, was popularized by these two papers here. And if you've ever used background cuts in Microsoft PowerPoint, that's what it's based on. I don't know how many people here actually use PowerPoint, but it's a fun tool to play with. So now I'm going to switch to binary energies, which are NP hard to optimize it, and to motivate why you might want energy which is hard to optimize even for such a simple task as segmentation. Let's look at the problem of segmenting an object which has thin structures. So here we want to segment this vessel structure, and it has many thin parts. So here, if you use Spot's model, you prefer compact segments, so you actually lose a lot of parts. So I'm not showing the data terms, but data terms here are quite reasonable. And if you play with parameters, this is the best segmentation you obtain, so you actually miss a lot of thin vessels. There are many ways to try to fix this problem. Curvature, of course, is one of very good ways to fix it. But simplest way to fix it is well, sort of alleviate, I wouldn't say fix it completely, but at least alleviate this bias to short boundaries, is to allow some use some weights, some penalties between nearby pixels to be negative. Because now if you have a negative penalty between nearby pixels for creating a boundary there, you're actually encouraging a boundary. So sometimes called attraction, repulsion. So you're actually encouraging to put a boundary between such pixels. So you might run like an edge detector or some other processor and say that whenever there is a high image contrast, you actually get something if you create a boundary. So you put a negative EPQ there. So if you do optimization with negative EPQs, you get much better results. So for example, if you zoom in on this area and that area, the difference is most obvious. You recover more thin edges. Unfortunately, once you allow for negative EPQs, the problem becomes NP hard. You can no longer solve it exactly, so we have to do some approximation. So in general, in pairwise binary energy, you allow some coefficients to be, some weights EPQ to be positive, some weights EPQ to be negative, and it's useful for many problems in computer vision, even for binary energies. So as I mentioned, segmentation with repulsion, for denoising, for image restoration, for curvature, for volumetric reconstruction. So it comes up again and again. So one thing you might try, and we have tried that, is to use some standard optimization methods. Those, for example, based on global linearization like QPBO, TRWS, and Vlad is here in the audience. Or you can do, some people have tried before local linearization, such as parallel ICM and IPFP. What we proposed in our work is to use local submodular approximation. So in previous work, they have used local linearization. We're going to do local submodular approximation. So we're going to approximate our energy function not with a linear function, but with a more general submodular function. That's the name, LSA. At each, we start, it's an iterative framework. You start with some solution, and you construct submodular approximation for your function at the current solution. You optimize that, and you continue until convergence. So there are two points here which distinguish us from previous work. Approximation we construct at each point is not linear, it's more general submodular function. And another thing is we control step size. We don't want to allow large step size from the current solution unless it's beneficial. So I'm going to use the schematic pictures. So to plot the energy, I'm going to plot x on horizontal axis and energy on the vertical axis. And even though all my plots look continuous, of course we're dealing with discrete energy, so in fact neither x, x is not continuous, neither our energy is a smooth curve, but it makes for nice pictures. So on this axis, when I plot x, actually x is a vector which belongs to this space. And the curve, even though it looks continuous, is not in fact continuous. So in order for me to show submodular function, I'm going to draw a convex curve, just because again it's easier. Submodular functions analog of convex functions in discrete optimization. So that's my schematic drawings. So again, we have not submodular function that we want to approximate. We start at some point x, xt at time t. At time t we construct submodular not linear approximation. So here's this convex function to show it. We minimize it, and then we repeat. So before I continue, I actually would like to switch to another form in the way I write pairwise interactions. Unary interactions stay the same, but pairwise interactions I'm now going to write algebraically, and you can write any binary energy in this algebraic form up to a constant. So the meaning, though, once you rewrite from the previous form into this form, actually the meaning of VPQs switches. Now it's Potts model if all VPQs are non-negative, not positive, and you can optimize energy with a graph cut, and your energy is difficult to optimize and not submodular if there exists a positive weight VPQ. So I've done this conversion, and now it's a hard energy if there is some VPQ which is not zero negative. And both trust region framework and auxiliary functions framework is very well known, sometimes under different names. In general math and in computer vision, people have used it, but not to optimize non-submodular pairwise energies. So we're the first to do that. So let me first talk about the trust region framework. So we're going to construct local submodular approximation, and we call this method therefore LSA-TR. And then I'm going to talk about auxiliary function framework. We do the same thing. We construct locally submodular approximation, which is also in upper bound. And this method is called LSA-AUX. So let me talk about let me first talk about locally submodular approximation. So we start at some point xt, we have two parts in our energy. We have submodular part. This part is the part we don't need to approximate. We leave it as it is. And then we have supermodular part. This part we need to approximate. So what goes into submodular part? All the unary terms are submodular. We don't need to approximate them. And in the regularizer, we have two types of terms, submodular and supermodular. So submodular terms we don't need to approximate. We put them into submodular part. Blue here, my blue arrows means submodular with negative coefficients go into the submodular part. No need to approximate. And the difficult terms, I'm using green arrow, and they go to supermodular part. And here I was very proud of myself when I made this picture, because blue and yellow, blue and green, when you add them, you get yellow. So these are the mixed terms, blue and green, and so this is denoted by yellow, okay? And I knew no one will get this joke, so I'm always telling, and all people always smile, okay? And I actually remembered the color combination, which I guess I should since I'm in vision, but I didn't. Okay, I wasn't sure, I mean. So how do we approximate how do we do our submodular approximation? So again, as I mentioned, the submodular part there is no need to approximate, so the unary and submodular pairwise terms stay the same, but supermodular parts we need to approximate, supermodular terms we need to approximate, and we're going to use linear or modular approximation for them. So supermodular energy is replaced by submodular approximation. And of course, we have to make sure it coincides with the current, with the true energy at the current solution. Okay, so let's look at linear approximation of supermodular term. So the supermodular term is going to consist of the summation of all the pairwise potentials which are supermodular. So for them, coefficients VPQ are bigger than 0. So it's enough to explain how to approximate one of them. And then you just add up all those approximations, and also without loss of generality, I can assume that the PQ coefficients are all equal to 1. Doesn't matter which positive constant. So let's look at this supermodular approximation. So I'm only interested, my function is discrete function, so I only have really 4 configurations, this 4 blue points here. So if I draw my function like that, it looks really poor and not pleasant to look at. So my function is 0 at this configuration, 0 here, 0 here. The only non-zero value is at 1. Both xp and xq are equal to 1, so it's equal to 1. And this is sort of like a really naked graph, so I'm going to dress it up a bit. I'm putting a continuous function here, xp times xq, just to sort of make pictures look prettier, but keep in mind that we are still really only interested in this, in approximating function at these 4 points. I haven't left the discrete optimization, just continuous drawing makes it nicer. So unary approximation will consist of unary terms plus maybe a constant. So also what you have to keep in mind, this unary approximation must be exact at current solution, and we have 4 possibilities for the current solution. This point here, this point here, this point here, this point here. So we have these 4 possible cases, and in each of these cases we construct a different unary approximation. So let's first look at approximation we use at this point. So xp here equals to 1, xq here equals to 0. So we use very simple approximation. We use approximation, approximate this with xq. And again, continuous drawings look nicer. So this is the green plane. If you look at it as a continuous function, and if you observe, this plane is exact in 3 out of 4 configurations. So it's exact. It gives us exact values for function xp times xq everywhere except that point here. At that point here, the value of this approximation is 1, where it should be 0. And similarly, for other configurations, for configuration, if current configuration 0, 1, we use approximation xp. I'm again drawing it with continuous plane. And again, this approximation is exact at 3 out of 4 points. It's exact everywhere, except that this point here where it should be 0, but in fact it's 1. For configuration, if current configuration 0, 0, we just use a flat plane. We just use 0, flat plane. And again, 3 out of 4 configurations are exact. And finally, if current configuration is 1, 1, we use the following approximation, which is this sort of bluish plane. And again, this approximation is exact everywhere at all points except 0. 0 should be 0, but it's -1. So we have approximation which is quite good, exact in 3 out of 4 configuration. And now we can now continue with this iterative optimization framework. So we have current solution, we construct our submodular approximation, and we could actually take a Newton step. We could optimize this submodular approximation, but if our step size is uncontrolled, we can be in a situation where at the minimum of approximation, actually the objective function is worse than where we start with. So we want to make sure that we never take such a large step size that the energy actually goes up. So in a common way to do this is the so-called trust region framework. So in trust region framework, what you do, you optimize your function not globally, but in some region which you call trust region, and you're trusting that in that particular region your approximation is accurate, not too far from the correct function. So we will have some trust region size which increases or shrinks, and now we have to solve this constraint problem. So we still have our approximation, we have our submodular and approximate part, but now we want to solve it just around the current solution within some region controlled by the t parameter here. Unfortunately, even and of course in my nice pictorial representation here, if you solve within this trust regions, just within your trust region, here is the minimum of your approximation, and it actually is lower than the true energy is lower than what you start with, so life is good. Unfortunately, even this trust region step is NP hard to solve in discrete optimization framework, so we cannot solve it exactly, we solve it approximately. So instead of putting this condition, we do something which we can actually optimize exactly in discrete framework. Instead, we replace this condition on the previous slide by adding penalty if our new solution is far from the current solution. So xt is current solution, so we put a norm. Usually we use like Euclidean distance or Hamming distance, and this distance, the penalty for deviating from the current solution, is controlled by parameter lambda t. So lambda t is something which controls, intuitively it controls the trust region size, although we're not solving trust region subproblem exactly. It's fixed at each iteration, and it's inversely related to trust region size. So the smaller is this parameter, the further away we allow him to step from the current solution. And this parameter is adjusted based on the quality of approximation. Okay, and you can implement this in discrete optimization using unary terms. And it's a submodular function. Okay, so now let me switch to the second type of methods, which we call LSA-AUX. So it's based on auxiliary function approximation. So it's very similar to the trust region, to LSA-TR. But now instead of approximate, so we have current solution. We approximate energy, but now we construct approximation which is also an upper bound on the true energy. And in this way, we don't have to control the step size. We can just globally optimize approximation because the true energy is guaranteed to go down since we have an upper bound. Okay, so so we need a different, previous approximation was not an upper bound, so we have a different approximation. So actually, two cases are exactly the same as before. If current solution is 1, 0, we can use the same green plane as in trust region approximation because it's also an upper bound. If our current configuration is 0, 1, we can use the same yellow plane as in the trust region framework because it's also an upper bound. And hopefully you can actually sort of see that the blue plane is above our function that we're trying to approximate. But in the other two cases, whatever we're using for trust region is not an upper bound, so we have to do something different. So we use, in the case when current configuration is 0, 0 or 1, 1, we use the following approximation, which is an upper bound. So we use xp over 2 plus xq over 2, and this is this sort of purplish plane which lies above our function. And in this case, only 2 out of 4 configurations are exact. So let's look at some results. Let's look at the segmentation results for segmentation with repulsion. So here we have an image, and here are the data terms we use for it. So remember, bluish colors means pixel wants to be foreground, and reddish colors means pixel wants to be background. And if we use PATS model, submodular function where all the PQs are negative, we have many thin structures missing. So now let's introduce edge repulsion, so allow some coefficients to be positive to encourage boundary in those places. Let's look at the results of QPBO and some versions of it. So whenever you see gray, it means QPBO wasn't able to label those pixels. So dark means vessel, white background, and here actually it didn't manage to do anything, and I'm not showing any energy because it didn't label many pixels. With the improved version of the algorithm, you do label all the pixels, and here's the energy. Here's the loopy belief propagation, slightly better energy than QPBO. TRWS, another of the Vlad's algorithm, which she said it's the same as TRWS, but doesn't give us the same energy in our experiments. I guess maybe the order of extracting final energy is a bit different there. I think that's why. Another method from previous literature which even gives positive energy, which is really way off. And here are our two methods, LSA-AUX and LSA-TR. So LSA-AUX gets better energy than any of the previous methods. LSA-TR gets energy. Okay. Sorry. LSA-TR gets much better energy than anything else. But now let's look at the time. LSA-AUX takes 5 seconds, LSA-TR takes 30 seconds. I should have mentioned why LSA-TR takes it's not always, but usually takes much longer, because you actually have to run graph cut problems several times for each iteration for LSA-TR, because as you expand the trust region size, you need to solve graph cut problems several times, where at each iteration of LSA-AUX you just there is no trust region size to change, so you just run graph cut one time. So that's the reason. Let's look at another application. So there is, in computer vision community, there's a data set for evaluating energy optimization methods run by Heidelberg University. And they have one case for non-submodular binary images, in particular for Chinese character in painting. So here you have input image where part was occluded, then you have ground truth, and then you have in-painted results. So here, the way to compare different algorithms on this data set is to see in how many cases, so there's 100 instances for this in-painting task, and the way to compare algorithms is to see in how many cases your algorithm was better than other algorithms. So here, let's look at this line. Here we have a LSA-TR method. It has average energy over instances, average running time for 100 instances, and then this number means that in 35 cases, it got the best energy in the 35 cases. Its rank is 2. The best performing LSA-AUX actually didn't do well at all. Its rank is 8, the lowest on this list. The best performing algorithm is this one, rank 1. It did, in 85 out of 100 cases, it obtained the best energy. But now let's compare the running time. So this algorithm based on sampling and its orders of magnitude, it's 2,000 seconds versus LSA-TR, which is a fraction of a second. Okay. So, and in this actually case, LSA-AUX is slightly slower than LSA-TR. I don't really know why, but in most cases, it's way faster. So, in general, for most applications, we have evaluated 5 applications. In general, LSA-TR works slower than LSA-AUX, but gets us better energies. So what you want to do, and again, the advantage of it at each iteration, you just have, the advantage of LSA-AUX is that at each iteration, you just have to do graph cut one time. So the question we had, is it possible to improve LSA-AUX somehow to still have a fast computational time, but make it obtain better energies? And this is the last part of my talk about things you can do to improve LSA-AUX. So let's go back and look at upper bounds we were constructing for LSA-AUX. So for the case when current configuration is 1, 0, we had a good upper bound, 3 out of 4 configurations exact. You cannot do better than that. For the case 0, 1, also we had upper bound which had 3 out of 4 configurations exact, and again, you cannot do better than that. However, for this case, when current configuration is 0, 0, 1, 1, we actually have an upper bound which only has 2 out of 4 configurations exact, and this is not as good as you can do with a linear upper bound. In fact, in this case, you can use both xq and xp as an upper bound. So xq was this green plane we've used for the case 1, 0, and xp was this yellow plane upper bound which we use for the case current configuration is 0, 1. So in fact, both of this you could use for cases when your current configuration is 0, 0 or 1, 1. The question is which one. So you would have to, when you have to implement your algorithm, if current configuration is 0, 0 or 1, 1, you have choice of 2 upper bounds for, let's say, AUX. I mean, you could use this one, but we know it's not as tight as possible. Or you can use one of those, but which one do you choose? So in fact, we want to look at some intelligent ways of choosing an upper bound, since we do have a choice. And the thing to keep in mind is if you use upper bound xp, it models configuration 0, 1 exactly. If you choose xq, it models configuration 1, 0 exactly. So one thing you could actually try is randomly. Whenever there's a choice, you might think that choosing randomly is a good idea. Just split a coin and choose either xp and xq. And actually it's worse than using this less tight upper bound. We have tried this before. And to understand why would it be not a good idea to choose randomly, consider, say this is our current configuration. When we're choosing an upper bound, we want our upper bound to be accurate for configurations which we think are more likely to occur, more likely to have lower energy. So now, whenever two nearby pixels are 1, 1 or 0, 1, we have to choose whether we're modeling configuration 1, 0 or 0, 1 exactly. If you split a coin, it turns out you model configurations like that exactly, but this configuration is very random. It has no coherence. We know our labelings are coherent in vision, so we want to model labelings. So the labelings we know are likely to occur as an answer to our problem. It's those labelings for which we want to have an accurate upper bound, but when we model things randomly, we have accurate upper bound for things like that, which is useless because we know they are unlikely to be an answer. So the question is, how do you make upper bound accurate for things which are more likely to be an answer? One thing is to look, we have two approaches. One thing is to look at energies. Another approach is to implicitly model a set of coherent nice labelings more accurately. Prefer to model those more accurately. So let's look first at adaptive bounds based on energy criteria, based on trying to figure out which configurations are more likely to have low energy in the true solution, in the optimum solution. So again, what we need to do is just when the current configuration is 0, 0 or 1, 1, then we have a choice of an upper bound, so we need to look at those. So we need to choose between two possible upper bound. Either you approximate this clique with xp, and this particular approximation models 0, 1 exactly, or we choose approximation xq, and this particular approximation models 1, 0 exactly. So the simplest thing you can do is you look just at the energy, and since you don't know energy of some labeling, and since you don't know the energy, you don't know the globally optimal solution, you look at some proxy of that. So here are two pixels which are nearby, and for them we're going to have to choose either this or that configuration. So we want to model more precisely configuration which is more likely to appear in optimal energy. So what configuration is more likely to appear in the optimal energy? Of course, we would like to have access to all of it, but we don't. We only have access to these two pixels. So let's look at these two pixels, and let's look at the simplest proxy for our total energy. Total energy, of course, is very, very complicated, but we can't deal with it. So we're going to look at a very simple approximation of the total energy, where we just look at the unary terms for these two pixels. So this is really dumb approximation, but it works way better than using just adaptive bounds like in our previous work. So simply what we're doing simply is looking at the energy of this configuration, where energy is just given by the unary terms of two pixels, and energy of configuration 0, 1. And if it happens that energy of configuration 1, 0 is less than energy of configuration 0, 1, then we want to, this is a more likely outcome for the optimal labeling. We're more likely to have 1, 0 in the optimal labeling compared to 0, 1. So we're going to choose bound which models this configuration exactly. Which bound models configuration 1, 0 exactly? It's the xq bound, which was something we have to keep in mind. And when we're debugging, that was pretty horrible to remember what was modeled exactly, what wasn't. In fact, we made one mistake when programming this, and it turned out that very rarely make a mistake and you actually get something good. That was the case. We made some bug, and we have an algorithm, a version of this adaptive bound, which actually works better than anything else. One problem, it took us then a month to understand why, but I'm going to skip that. But sometimes I do tell students, once in your life you're lucky, and a bug gives you great performance. Okay, so so this is a really simple approximation to our energy. So we can look at something a bit more complex. For example, instead of using this approximation, we can also look at pairwise terms involving pixel spin Q. Of course, if we knew what values these neighbors of pixel spin Q had in the optimal labeling, we should have been using those, but we don't have access to that. So we're going to use current labels of pixels of neighbors of pixel spin Q. So you can look over all neighbors R of pixel spin Q, and since we don't have access to the optimal solution, we're just going to use the current values. So it's very similar idea to the unary terms, except now you also use pairwise terms. You use immediate neighbors of pixels P and Q, fix their values to whatever they are in the current solution, and then do exactly the same thing. You compare whether this configuration has low energy or the opposite configuration has a low energy. And this is again your proxy for what the optimal labeling would prefer. And you do exactly the same thing. If this configuration gives you low energy, then you prefer modeling with XQ, because XQ models 1, 0 exactly, otherwise you model 0, 1. So these are the two things, two types of adaptive bounds based on energy. Another idea how you can try to choose an adaptive bound intelligently is to encourage set of coherent solutions, spatially coherent solutions, to be modeled exactly. So let's take current solution. Suppose current solution is this blob here, and this is its boundary. So inside it's background, it's foreground, outside it's background. And let's ask a question: what would be a coherent set of solutions that we could get starting from this current solution? Well, if you look at if you take the distance transform, we could actually model all solutions exactly which lie along the contours of distance transform. So all these level lines, solutions which correspond to the level lines, we could model exactly, and this would give us a set of spatially coherent solutions. And the way to do it, whenever you have a pairwise interaction between two pixels in the direction of the distance transform, we model 1, 0 exactly. Because if we model 1, 0 exactly, then the boundary lies between these two pixels. It's modeled exactly. So this gives us a set of solutions which are coherent solutions which are modeled exactly, and not just those along the level lines. So in the schematic illustrations, I'm showing blue is a current solution, so this possible solution is also modeled exactly. And even for things which are not modeled exactly, we still have an upper bound. So here, this section is not modeled exactly, this modeled exactly, but this part is upper bounded, so we still fine with using auxiliary cuts. And again, here, for solution like that, large part of contour, all the green parts are modeled exactly, red ones are overestimated. But again, we are an auxiliary function framework, so things will be still, we will still go down until convergence to local minimum. We combine, by the way, combine this coherence of contours criteria with other criteria, like we can add unary preference. I've talked about to this one before. Another idea we have is, which was sort of inspired by this distance transform idea. If we have a current solution, what we can do, we can model exactly changes of boundaries in a certain orientation. So we came up with what we call compass moves. So we can model orientation which is sort of right and above exactly. So let me explain. It's a pretty picture, but I know it's not really clear when you stare at it. So if you take any pixel in the non-shaded area and connect it to any pixel in the shaded area, we can model switch from 1 to 0 in that direction exactly. So it maybe it's more helpful to look at what boundary changes we can model exactly with this particular move. So if this is our current solution, any change of the boundary which goes that way or this way, that way, it can also grow, but I don't know why I didn't. We should have done a picture where the boundary grows. So any change of the boundary in that particular orientation, we can model exactly. So of course, one orientation is not enough. We have 4 possible discrete optimization, so we can alternate between these 4 directions. So it's like you start with some counter, and you can change the boundary in different orientations exactly. Okay, and then there are some other variants. We have, one of them was done by a bug, which I don't have time to talk about. But let's look at some results now. Let's come back to Chinese character in painting. So LSA-TR was the best of our method, although it's still not the best one overall. So, but now LSA, this version, we have several versions of adaptive LSA-AUX. Now this particular version with distance transform plus unary terms performs the best. It finds the best solutions in 33 cases now, whereas this one is only 16, and running time now is even slightly better than before. And of course, this Monte Carlo based method is still the winner, but again, huge running time. Curvature optimization. So we have in our previous work model where we have a binary segmentation with curvature. So with PATS model, you get something like this. With curvature, this is input image. PATS model gets rid of thin objects. With curvature, you can keep them. So let's look at the performance. It's useful to look at the performance versus where you vary the strength of the curvature regularizer. So here is the strength of curvature regularizer. It increases that way. Here's the energy. Let me remember what these plots are. So LSA-TR used to be the best, way better than LSA-AUX, and here it is. But these 3 variants of our adaptive bounds do much better. So this is something I've talked about. Again, distance plus unary terms plus something else on top of it, which I'm not going to talk about. And this is the buggy method. Well, I mean, we now have a good explanation, but this is the purple one, is the one which came out of a bug and some variant of it. They do now much better than LSA-TR for all values of regularizer strength. How much time do I have? 5 minutes. 5 minutes. Okay. Also, we have played with shape priors. You can take a shape prior. We have a certain type of shape prior which encourages boundaries to be in certain ways. In our previous work, we had so-called compact shape prior, for which you have to give a center, and then around the center you say in which way boundary should be oriented. So here it should go up and to the right, down and to the left, and so on. Now we have generalization of the shape prior where you don't have to give a center. You just say, I'm looking for an object where the boundary first goes this way, that way, this way, and that way, and you don't have to give the center. And even though it's originally, in its initial formulation, it's a multi-label problem, we can convert it to a binary problem. So let's see what are the results here. So we have input image, user puts some scribbles, they want this object which follows our shape prior. And if you look at the previous methods, nothing really comes close to getting good solution. Here's LSA-TR, which takes 31 seconds and it cuts off part of the object. This is the solution we find with our auxiliary adaptive method. Energy is slightly lower, we get the full object, but the running, okay, maybe the difference in object is not so large between the two, but the difference in running time is much better. So we evaluated this adaptive adaptive LSA-AUX on 6 applications, and what's interesting is that there is no single version. We have probably like 8 different versions. I lost count of how many versions we have because we just sort of kept coming up with sort of interesting heuristics on how to choose bounds adaptively, and not a single version dominates all others. So it seems like for each type of the energy, due to particulars of that energy, one of the heuristics will work better than in other. But in all in 5 out of 6 applications, actually every single version of our adaptive LSA-AUX was better than LSA-AUX. Whatever we did was better than random, except one application. Because again, you don't want to model random labelings well, you want to model labelings which are actually likely to be in your optimal solution. And at least one version of LSA-AUX adaptive was always way better than the not adaptive version. In 4 out of 6 versions, our LSA-AUX adaptive was better than LSA-TR, and in 3 applications it was strictly better and always faster. So I talked about effective discrete optimization methods for general pairwise binary energies. I've talked about 2 methods we developed in older work and extensions of this method, which makes it faster and even better than the first method here. So we get state-of-the-art results on most applications, and the code is available online, not for the adaptive part of it, I believe, because it's more new, but for these 2, the code is available online.
Are there any questions or comments?
So in your test, some of the V should be positive. So how do you choose it for the test you did in the very beginning?
So for the thin vessels, we chose pixels. If 2 neighboring pixels had intensity norm of the gradient greater than some threshold, we set it to negative. It was just some sort of function which keeps some of the weights positive, some of them become negative if the gradient is large enough. In our experience, so like there is a whole community of people who do correlation clustering, and they know how to set these things much better than we do. In our experience, it was quite, I wouldn't, for these structures, I wouldn't necessarily recommend this approach. In our experience, it was quite fragile. You had to be really careful about setting that threshold, but it's the easiest, for me it's more like, well, first of all, there's a community of people who actually like doing that type of segmentation with negative weights. But second, it's very easy for me to motivate non-submodular energies because I start with segmentation with paths model where you encourage short length, right? And then that tells you why you'd want non-submodular energies. Yeah, but basically it's by a lot of hand and trial and fail. Yeah, nothing intelligent there. Yeah.
Another question that is it true that your energy is a convex function minus another convex function?
Yes, yes.
So then I think there are some recent works which can use trying to do global minimization for differences of convex functions. Do you think you can use some of their methods to?
So in fact for the trust region framework, no, but for the auxiliary functions framework, yes, in fact, we have, after we submitted the work for auxiliary functions without the adaptive part on it, we discovered some previous work, even in discrete optimization community. So what people have done before us at the point of application was the random choice. So actually I say we tried random choice, but we traced back the previous work where it turns out what they've done before was, no one has done it for binary energies anyway, but if you apply what they've done for binary energies, you would end up randomly flipping a coin, which is a bad idea, in our experiments at least. And intuitively it's a bad idea, yeah. But yes, the answer, short answer is yes, we tried, but it's not, it doesn't work quite as well.
There was another question, no?
All right, well, I have just when you formulated your energy, it consists of 2 terms, one is quadratic, another is linear, right?
Well, pairwise, I prefer pairwise and linear, but sure, quadratic and linear, sure, yeah.
Right. Well, in linear term, you have some kind of information about images. So some pixels would like to ground pixels. How did you get that preliminary information?
For that particular image, I think it was done. There are various ways you can do it you could do it through learning. You could do it through prior knowledge. In that particular example, I believe it was done through user interaction. User marked some points on the object, some points in the background, and you construct histogram and you model it based on the histogram. I believe I actually would have to ask Lena how she's done it. But through learning and through user interaction, are the two most common.
Okay, so I have a question related to this about this first term. In some of the examples that you gave, this first term, the red and the background and the blue and the red and the blue, if you would do just thresholding, you would get a superb result, you know, for the vessels image.
Well, you have to know where threshold lies, right? So there was
So just show us the image with
for the vessels. I'm pretty sure we tried just
so
threshold.
That's the first one. Before you showed the thing that influences the first term.
Sorry, I keep going home, which is not a good place to go. So I'm pretty sure, so the data terms are strong, but not strong enough to do it by just thresholding.
Just before.
Here.
Yeah, here. You see here, I have the feeling that if I take like anything that has some blue in it, I would get a performance which is superb. Because you know everything.
Right. So you have to, in this visualization, you have to know where the threshold actually lies, where it starts switching from dark to light. So I'm pretty sure that you wouldn't get perfect segmentation here by thresholding. Well, first of all, yeah. So like, I mean, again, maybe we should have separated the picture. A better visualization would be the positive ones and the negative ones, because then you could see what thresholding would get you. But you know, we were, I believe, careful in our experiments. I cannot have to talk to Lena, but it was not.
So that's related to the second question here. Are there any comments or questions? Some more? Good. So thank you very much, and thank